Let's dive into the fundamental building blocks of matter atoms. Atoms are the basic units of matter that make up all substances. An atom consists of a central nucleus containing positively charged protons and neutral neutrons, surrounded by negatively charged electrons. The three main components of an atom are protons, which have a positive charge and are found in the nucleus, neutrons, which have no charge and are also in the nucleus, and electrons, which have a negative charge and orbit around the nucleus. Electrons orbit the nucleus in specific energy levels or shells. Each shell can hold a specific maximum number of electrons. The number of protons in an atom's nucleus defines its atomic number and determines which element it is. In a neutral atom, the number of protons equals the number of electrons. Isotopes are variants of an element that have the same number of protons but different numbers of neutrons. This affects the atom's mass, but not its chemical properties. Ions are formed when atoms gain or lose electrons. Atoms that lose electrons become positively charged cations, while atoms that gain electrons become negatively charged anions. Understanding these basics of atomic structure is crucial for grasping how elements interact and form compounds. The periodic table is a systematic arrangement of chemical elements, organized by their atomic numbers, electron configurations, and recurring chemical properties. The periodic table organizes elements by increasing atomic number, which is the number of protons in an atom's nucleus. Elements are arranged in rows called periods and columns called groups. Elements in the same group share similar chemical properties. Elements within the same group share similar chemical properties because they have the same number of valence electrons. Valence electrons are the electrons in the outermost shell of an atom. The periodic table displays several important trends in atomic properties. The three main periodic trends we'll examine are electronegativity, ionization energy, and atomic radius. Atomic radius refers to the size of an atom. As we move from left to right across a period, the atomic radius decreases. This is because each additional proton increases the nuclear charge, pulling electrons closer to the nucleus. As we move down a group, the atomic radius increases. This happens because each new energy level adds another shell of electrons further from the nucleus. Electronegativity is the ability of an atom to attract electrons when forming a bond. As we move from left to right across a period, electronegativity increases. This is because atoms with more protons have a stronger pull on electrons. As we move down a group, electronegativity decreases. This happens because the valence electrons are farther from the nucleus and experience less attractive force. Ionization energy is the energy required to remove an electron from an atom. As we move from left to right across a period, ionization energy generally increases. This happens because the increased nuclear charge holds electrons more tightly. As we move down a group, ionization energy decreases. This occurs because the valence electrons are further from the nucleus and are more easily removed. Understanding these periodic trends helps us predict how elements will behave in chemical reactions. Elements with high electronegativity, like halogens, tend to gain electrons. Elements with low ionization energy, like alkali metals, tend to lose electrons. These tendencies determine how elements will form bonds and react with one another. Recent advances in atomic research have revolutionized our understanding of elements. Modern experimental techniques have dramatically improved our ability to study atomic properties. Laser spectroscopy enables highly accurate measurements of atomic states. Ion traps and electron beam ion traps allow researchers to study charged particles with unprecedented precision. Theoretical modeling has greatly improved with methods that accurately account for relativistic and correlation effects in complex atomic systems. Super heavy elements research is pushing the boundaries of the periodic table. Scientists are working to synthesize elements with atomic numbers up to 122. Flerovium, element 114, shows interesting relativistic effects that enhance its stability through a quasi-closed shell configuration. Research now focuses on ephemeral nuclei, which exist for incredibly short periods, some lasting mere picoseconds. These studies challenge our understanding of what constitutes an atom and provide valuable insights into nuclear astrophysics. The future of the periodic table includes continued synthesis of superheavy elements, with scientists searching for the theoretical island of stability, a region where superheavy elements might have longer half-lives. This island of stability is predicted to occur around elements with approximately 184 neutrons, potentially creating nuclei that are dramatically more stable than neighboring elements. Artificial intelligence and machine learning are revolutionizing element discovery and analysis. These technologies accelerate research by processing vast amounts of data and predicting properties of yet undiscovered elements. AI accelerates data analysis from complex experiments, helps predict properties of undiscovered elements, and optimizes experimental conditions to increase the chances of successful synthesis. Ongoing research into superheavy elements and advanced computational methods continues to expand our understanding of the atomic world and the limits of the periodic table.